Let's look at this thing. Now, this thing is not an enol. You may recognize it. It does have a double bond, so it's an ene, but it's an ene-amine. And so there's something missing from the Lewis structure of this enamine that I'd like you to fill in that really reminds us how closely related this really is to an enol. So what is it? What's missing from this Lewis structure? Fill that in. The thing that I left off is this pair of electrons on nitrogen. And so the reason that that pair of electrons is important is that this double bond, and let's remember that there's a vinyl hydrogen there, this double bond is going to be particularly nucleophilic because when it acts as a nucleophile, the carbocation that gets left behind is resonance stabilized. So what I would like you to write is, what would you expect to happen when this enamine reacts with some sort of electrophile, which I'll just represent it as E+, but it could be something like an alkyl halide or some other type of electrophile. So what would you predict would happen here? Nucleophilic double bond, electrophile. The arrow pushing would come from here to there. And so now we need to make a decision. Does the electrophile get attached here, or does the electrophile get attached there? There are various different analogies that we could make. We could make an analogy to the mechanism that we just looked at in terms of enol-keto equilibration. We could also think about electrophilic aromatic substitution. This is not a benzene ring, of course, but you could imagine a benzene ring there. And we know that an amino group is an ortho-para-director. And the reason it's an ortho-director is that the positive charge can be resonance stabilized. Okay? So if you didn't get this far, pause the video, draw the other resonance structure. The other resonance structure just shows how the nitrogen lone pair can get involved in stabilizing this reaction product. Looking at this resonance structure, what type of functional group does this look like that you know about from your previous study of aldehydes and ketones? It looks like an imine. An imine has a carbon-nitrogen double bond, except it's not an imine because there's this positive charge on the nitrogen. So we'll call this an iminium ion. It's a cation. So I want you next to imagine that we get this far, and then we treat this product with water and say a catalytic amount of H+. So what would you expect to get if we work up this iminium under those conditions? That's the last part of this question. Well, we know that imines can be hydrolyzed to the corresponding carbonyl compound. So the final product is going to have a carbonyl here. And there's going to be the E at the alpha position, the electrophile. And then the other product from this reaction is going to be the corresponding amine. And then under the acidic conditions here, we might reasonably draw the amine as this ammonium type of ion. So look at overall what we've done. Overall, we have attached an E alpha to the carbonyl via an enamine. It actually turns out, as perhaps we'll have a chance to discuss in class, that this type of enamine mechanism is used by nature to do aldol type of chemistry in some cases. So the electrophile here can be a variety of things, including an electrophile derived from another aldehyde or ketone molecule. So the enamine being used as a nucleophile to get to these sorts of keto products that have an electrophile attached at the alpha position.